Okay, welcome to the Cosmic Pie podcast here on Tuesday, February the 14th. So I'm Wayne Barkhouse, and today with me again is...
Robert Moore. Nice to meet y'all.
We're broadcasting live here from the campus of the University of North Dakota in Grand Forks, North Dakota. And to start off, I just wanted to mention that we do have a live chat that's running. So if you have any questions at any time during the podcast, please feel free to type us in a question and we'll answer as soon as we can and in the best of our ability. Also, I'd just like to thank at the start the University of North Dakota, the College of Arts and Sciences, and the Department of Physics and Astrophysics for allowing us to do this. And also, as we always like to say, a disclaimer, any of the opinions or thoughts expressed by your hosts are those of the host and not necessarily of the university, the college, or our department. Now, Robert, today is February the 14th. That's Valentine's Day.
Yay! Happy Valentine's Day, everyone.
Now, you did wear a red shirt, I noticed, for the occasion.
Completely by accident. I just decided to wear some color today, and happens I had a red shirt. It caught my eye.
Now, I got a really profound question for you, Robert.
Oh, Lordy. Okay.
You ready?
Ready?
Do aliens have hearts?
Okay. The answer I have to come up with is they have to have something similar, yes.
Okay, so the next question is, are there aliens?
Now that sounds like what we're going to get into a little bit of today. Okay, so
Robert, the first real, if you like, search for extraterrestrial intelligence, right? SETI, as we call it nowadays, the search for extraterrestrial intelligence, that really began in the early 1960s by Frank Drake. If you want to show some information to people regarding that.
So there we go.
So Frank Drake, if you like, he started this process by observing two stars. You can see some information. There's Frank Drake. Frank unfortunately passed away last year. Here's he in front of a radio telescope in Green Bank. And one of the things that he did in 1960 was to start what's called Project Ozma. And really it was a project to listen for radio signals coming from two different stars. The wavelength he picked was 21 centimeter. Do you want to tell us why 21 centimeters and not some other wavelength?
I don't know the specifics, but I would gather there is no natural phenomena that broadcasts at 21 centimeters without it just being lost in the noise, the background of the stars. Like hydrogen does, a particular wavelength in the radio bandwidth. I forget what that wavelength is, but you don't want to be looking where you've got a hydrogen signal.
Right, and actually, if you're observing at 21 centimeters, that is where the hydrogen signal is.
Oh, that's the hydrogen line. Well, you see, I blew that one completely.
Well, if you want to be precise, it's 21.1 centimeters, approximately. But so that's, in some sense, that's a criticism, right, of the project. And
right.
It's really, the idea is we have to think very carefully of where you want to broadcast. Right. So if you're listening to signals coming from an intelligent society and they're broadcasting over some wavelength range, are they going to broadcast where it's quiet? That is, the background noise, if you want to call it that, is the smallest. So therefore, it's much more easy to detect your signal.
For all of us old folks, there used to be snow that would come on late at night on the TV. That's the background radio signal that we just have. And then you impose a signal on top of that. And that's what you really were wanting to see. We do have a question, by the way.
And what's the question? Okay.
From Mizuho Swam. Several years ago, Dr. Jaff lectured us. He passed around what was supposed to be a pre-solar rock. How would he be able to conclude that?
Right. So obviously you want to check the mineral, the composition of the rock itself.
Right.
And we know that the solar nebula would have a certain primordial mixture of material. In fact, you can look at things in our solar system that haven't been altered much, if at all, since the solar system began over 4 billion years ago. Those things would include potentially asteroids, for example. Right. You can even get measurements of the gas that's in the atmosphere of Jupiter and Saturn. Some of that is close to being primordial, but not all the way. So that's how you get abundance of deuterium and other elements and helium and so on. And so that's how I would do it. You would look at that and see if you can see And if it's has roughly the same abundance of the sun, right? Because the sun itself is going to be formed from the same material that the rest of the solar system is formed from.
And you're almost dead on target. There are actually items inside of asteroids and meteorites that hit Earth called chondrules that have solar abundance in them. So we know those are primordial units.
Right.
And so, yeah, that's exactly how you do it.
Right, and some of those objects, smaller version of them, had landed on the Earth as meteorites rather than meteoroids. And the chondrules inside of them can be analyzed. In fact, you could think that the outer surface of the rocks, as they penetrate through the Earth's atmosphere and get heated up, so they're affected, right? Their composition will change. But deep inside the rock, you can drill down inside the middle of the rock and that be less affected by the going through the atmosphere and other different processes that they might have undergone, space weathering type of thing, right? Before they intercepted the Earth.
This is also one of the reasons why we like looking in Antarctica, where there's less weathering and contamination processes because it's cold and no liquid water and to percolate into it, things like that.
And the other interesting thing about Antarctica
is it's all white.
It's all white and very easy. If you see a rock laying on an ice sheet in Antarctica, where did that rock come from? Most likely it came from above, not from below.
Right.
So it's much easier to find meteorites when they're laying in Antarctica than it is in almost any other place in the world in that sense.
It's starting to sound like another show.
There you go. But the observations that were done, getting back to extraterrestrial intelligence, that were done in the early 1960s by Frank Drake, he stared at two stars for over the course of several months, from about 150 hours or so. And he just picked two sort of, in some sense, random objects. I mean, there's a lot of stars that you can pick out of your sample, and so you just pick two. And the idea back then is we didn't know, for example, whether intelligent life was abundant everywhere in our galaxy. In fact, all we had to do was start to listen to any star, and the odds of picking up a signal may be great, right? It may be 100%. But so you have to do that experiment. You have to observe. You have to look. And unfortunately, when we look, depending on how you think about it, we didn't detect anything. And that's still been the case up till today.
Right. That's still the case. But it's interesting and it's neat to look at it. So, and I will point out that I think both of these targets have now been found with exoplanets. I know Epsilon has Epsilon Eridani, the second one, and I'm not sure about Tau Ceti, but I think it's been found to have an exoplanet around it too. So,
and of course, Frank Drake didn't know that in 1960.
He definitely did not know that. So, go on to the next slide. Okay. So, here's his famous equation, the Drake equation. And a caveat that has to be done here and should have been done for any of this discussion is while we can approach it using scientific principles and scientific ideas and concepts, in the end, any talk about life outside of Earth, much less intelligent life, is rife with speculation. So this equation in and of itself is already a speculation. It's a numerical method of trying to show here's the probability, here's the number of civilizations that we might expect if these are the right fractions and proportions to put in there. So that said, I guess you have a few things you want to say about it?
No, I mean, a lot of these are so uncertain.
Right.
And that, I mean, people, when you see an equation, you think, of something exact, right? It's just a matter of plugging in the numbers and then calculating the answer to it. But when Frank Drake, and people talk about the Drake equation a lot, Frank Drake and others have said over the years that this wasn't meant to be a formal equation that you would see in math or in physics or science in general, that basically it was an idea to gather things that we should know that would increase our understanding of what are the odds, for example, of intelligent life elsewhere.
Right.
So do you want to describe some of these factors?
All right. I like starting with those first three for the simple reason that those first three, we have some means of finding out what they are. So the first four, capital N is the number of transmitting, radio communicating civilizations out there. That's what we're after. R with the little star, we call it in fact R star, is the rate of star formation in the galaxy. Okay? So that we can get a pretty good handle on because we can look out with our telescopes and radio antennas and things like that, and we can get a pretty good handle on how many stars are being formed in the galaxy at any given time. So then there's F sub p, or FP. This is the fraction of stars with planets. Well, when Frank Drake first proposed this equation, that was a complete speculative thing. We had a sample size of 1, and one solar system, one star with planets, and at the time it had 9 planets. And what do we do with that? But we've got a lot more information now. There's over 5,000 detected exoplanets, all of them fairly close by. But it gives us enough information to be able to say, for every star out in the galaxy, there's almost certainly at least 1 planet. So we can get a fairly good handle on that number. And then comes N sub E, or NE, and that one is the number of those planets that a star has that are suitable for life. So that Goldilocks zone, that habitable zone. Now, something that's often not included in this speculation is, because this one is a little more touchy, we're beginning to find some planets in those zones, but we also find a lot of gas giants, which would preclude any terrestrial rocky planet where you would expect to find life, or where we would at the moment. That may be a bias. Where was I going? Oh, yes. But these gas giants may have large moons. For instance, 2 of Jupiter's moons, if I'm not mistaken, are larger than Mercury. So these gas giants may have nice, rocky, terrestrial, large-sized moons that would be suitable then, because they are still in the habitable zone, for producing life. So those 3 numbers, we can actually kind of start saying they're in this zone, or they're this value, and we can do more than speculate with those 3. So I kind of like starting out pointing that out. And then we get into the final 4. FL, or F sub L, is the fraction of those planets in the habitable zone that have life form on them. And then F sub I.
Can I interrupt you for a second, Rob? So the F sub L is the fraction of planets that have life on them, but that life could be any form, bacteria all the way up to intelligent creatures, right? I mean, a dolphin is intelligent, but a dolphin has a hard time trying to build a radio telescope.
Right.
So we have to be a little careful, I guess, how we parse through all of that. But other factors here are required to do just that, right?
Yes. And in fact, that's what those next 2 fractions, Fi and Fc, are about. If the planet develops life, what fraction of it produces an intelligent species? And then beyond that, even if you produce intelligence, I mean, it could be argued very definitively that dolphins, crows, chimpanzees, these are all intelligent species. But they don't do that final FC, which is produce radio telescopes, radio transmitters, radio receivers, and transmit detectable signals in the radio wavelengths that we'd be able to find. So FL, Fi, and FC, the fraction that have life, the fraction of those that produce life that have intelligence develop, and then on top of that, they have to be able to communicate, which I will also add. There's another problem with communication. Even if there were like humans, we stumbled on radio transmission. I mean, it took somebody having a wire with a little gap in it for them to detect that there was even such things as radio waves. So that may not be common in and of itself. They may have rockets and not have radio waves.
Well, from that point of view, you can think of Maxwell's equations. So it was really James Clerk Maxwell who united electricity and magnetism and formalized the interaction of the two into today what we call electromagnetic radiation. And then it was later on that it was experimentally verified that it was the waves that you can be produced from oscillating electromagnetic fields, and then that's what we mean by light, of course.
Right.
And therefore, you could test that by building a transmitter and a receiver and so on. And so that was done after the theoretical work was done. But of course, there was a lot of experiments and demonstrations that came before Maxwell, like Michael Faraday and so on and others, who demonstrated, a connection, an intimate connection between electricity and magnetism. And for those of you who want to understand that point of view, how can electricity and magnetism be related to each other? It's a very simple type of demonstration you can do. For example, if you have a compass, you can take a battery and a wire and just attach the two ends of the wire to either end of the battery. And if the wire is near the compass, you'll see the compass needle move. So the only way that compass needle move, which is really telling you what the direction of the local magnetic field is in the vicinity of that compass, the only way it can move is because another magnetic field must have been generated. And that's the flow of charges when you first touch the wire, the accelerated charges through that wire. Now, so that's electricity. So electricity, the moving charges produce a magnetic field and they reinforce each other, and that's what we see as electromagnetic radiation. And so any intelligent life form would have to master that.
Okay.
And we're assuming, of course, with good reason, that the laws of physics that operate locally here on Earth and in our vicinity are the same laws of physics that would operate light years away from us.
And that's an excellent point because, I've been in the arguments with people over, how can you assume that? And it's like, because we see the same things happening throughout the universe, it's a good assumption.
That's right. So a specific test on that, for example, is just to look at the spectrum of different stars and even galaxies. And some galaxies, they're literally billions of light years away. So you're seeing them not only at a great distance, you're also seeing them way back in time. And we see the things we expect to see when you look at the spectrum. The atoms, the laws of quantum mechanics operate the same way. We have never found a discrepancy in that. And so we can put constraints on the fact that the basic fundamental constants of nature and the way things operate in terms of the physical laws seem to operate not only locally, but also globally, which means in this case, of course, universally, but also for all of time, right? We go back, 13 billion years in the past, and the laws of physics seems to operate the same way back then as they do now. And you can't make that assumption, of course. You have to go do the experiment. You have to do the verification of that. In fact, there are very famous scientists in the past who have looked for variation in, for example, the gravitational constant, that capital G, and other things, for example, looking to see if we can determine that it varies with time or that it varies depending on location and those kind of things. And so far, they seem to be rock solid, that there is no variation. But we can test those things.
We can test them.
We don't have to assume anything.
Right. And so far, tests bear out. The laws of physics are the same everywhere in the universe. So
now we'll assume that there's some fraction of life that becomes intelligent enough that they develop these radio transmitters. So what other factor do we have to worry about, Robert?
All right. That brings up the final one, capital L. Capital L is the lifetime that the intelligence is transmitting for. Okay? Now, a lot of people take that to mean this is the time frame before they destroy themselves. Well, that's one thing that could happen. We're definitely a species who could destroy ourselves. And our lifetime, who knows what it'll end up being. But, there it is. But it also just means we're also a species who's going radio quiet. By that I mean when we first developed radio transmission and started broadcasting radio transmissions and television transmissions, we did it in a way that's called omnidirectional. The broadcast was just done in every direction, including up into space. Okay? But as we've gotten better at this, it is more efficient if you beam the signal where you want it, which is here on Earth, right? So the lifetime may just be the lifetime before when they figure out how to direct the signal where they want it to go, and so stop beaming it into space. And for us, that's going to be roughly about 100 years, which I'll get back to that when we start playing with this equation a little bit.
Right, you think of the time, way back, I don't know when it was common where if you received a television signal, it was through the air, through an antenna that you picked up the signal.
Right.
And then, of course, the great invention of cable came. And then with the invention of cable, then people could feed that signal then through a wire, and you didn't need necessarily to broadcast it through the air. And of course, nowadays in our society, we get the fiber optic cables, and it just becomes, from an energy point of view, much more efficient to broadcast things through optical fibers to have rather than through the air. And so a lot of that noise, which would be noise, outside of the Earth, right? The stray broadcasts that leak out through the ionosphere and so on. A lot of that, you're losing energy. So we don't want to do that. We like to be able to transmit information the cheapest possible.
Right.
That's one of the considerations. So how long does that phase last?
How long do you last in this phase of just throwing it out everywhere?
Right.
And yeah, so we've got to take that into account because we might be missing them because they're now quiet.
And of course, that does not consider the situation where you want to let people know that you're around, so that you purposefully broadcast a signal out into space with some type of message in binary format or whatever would be the way you would do it, to let people know that you're there and to say, hey, we're over here, we want to start up a conversation, and that would have to be transmitted by radio waves, of course, to be the fastest way to do that.
Right.
But then that some people would be scared of doing that, saying you just never know what's out there. So it's the old analogy that people have talked about a lot, like Stephen Hawking and others in the past. Do you really want to yell when you're in a jungle at night to let other creatures know that you exist, that you're there?
Because they may not be friendly.
That's right. And so we always have to worry about that to some extent. So it's interesting from a political point of view that people have suggested, I think we mentioned this before on our last podcast, is that is it really the responsibility of an individual person or a country, for that matter, to go ahead and do this sort of broadcasting and let potentially other life forms know that we exist? Or is this something that should be approved by the United Nations so that we, the people of the Earth, do this together rather than individually?
And right.
So that's an interesting debate. I'm sure that will happen a lot more in the future going forward.
Right. And because I'm one of those that it's like I fall in the camp of Stephen Hawking. I don't know that we want to be shouting because, I always point out to people, how much intelligence does it take to sneak up on grass? So any intelligent species is almost certainly going to be a carnivorous or omnivorous species, which means a predator. Do we really want to broadcast our presence to another predator that might come and want to be in our environmental niche? Because one of us is going away, because that's what happens when you do that. And by the same token, then, I know who my odds are. They crossed interstellar space.
Well, let's assume they visit us, right?
Right, that's assuming they visit.
They visit. But here's another argument. Even if they haven't visited, think of it this way. The Earth has been around for about 4.5 billion years. Mm-hmm. And that's just not a speculation. We can show through radioactive dating of rocks and so on that that's the age, of the Earth. And we assume the Earth formed at the same time as the rest of the solar system, approximately, including our sun.
Yeah. Let me interject here. When we say radioactive dating of the rocks, we are not speaking of carbon dating.
No.
Carbon dating, the antagonists against that are correct, is only good for about 57,000 years. But there are other radioactive elements like uranium, which has a half-life of around, 4.5 billion years. So there are dating mechanisms other than carbon dating. So we are not referring to carbon dating when we talk about this. Sorry,
No, that's right. And so what that means is when you think about the universe and its rate of expansion, we can work back how old the universe is. We have a pretty precise indication of that it's on the order of about 13.8 billion years old. So just think of it for a moment. The universe is 13.8 billion years old. The Earth has been around for 4.5 billion years. So that means that the universe has been around for on the order of roughly about 9 or so billion years before the Earth even formed.
Right.
Now, let's assume some planet formed around some star, and that planet had enough material, that is, its composition was conducive for the formation of life. However that happens, we don't know how to go from something that's not alive to something that's alive. I mean, that's an area of research that people are working on today very actively.
That's chemistry that I'm like, no, I'm not touching that.
So since the universe has been around for about 9 billion years before the Earth came into existence, let's assume it took 5 billion years. I'm just making up a number. Okay, a generous number. It's not a year, right? It's not a million years. It's going to take several years for life to first arise, let's say, somewhere else.
Right.
And let's say that took 5 billion years for life to arise somewhere else. It's roughly what's here on Earth. And to develop technology that they can broadcast signals out into space. So that life form has been around then for about 4 billion years after they got to the stage that we are at approximately in our advancement of technology and so on. So what type of advancement would we go through in the next 4 billion years to match what this life form has today?
Today.
You see?
Right.
So how advanced are they?
And that's a good question.
Okay, if they even exist. Of
If
course,
they
that gets
exist.
into a lot of these other factors.
But that gets into something we're going to discuss
Right.
here.
Do they annihilate each other? All of these kind of things. And so one could wonder that there is life forms out there, and they've been around billions of years. They have billions of years of head start. What would that look like? Now, that's very interesting when you
Right.
think of it from that perspective. So from the Drake equation itself, Robert, do you want to tell us about what this means in terms, statistically then, what do we expect in terms of the different intelligent
Sure.
life out there?
I played around with it earlier, so I brought up this slide, which gives the equation and what each of the the factors mean. I was trying to fumble for the word there, sorry. And I also looked up the volume of the Milky Way galaxy, which is about 17 times 10 to the 12th, or 17 trillion cubic light years, which a light year is a measure of distance, not time. It is the distance that light travels in 1 year. It is roughly, what did you say?
About 6 trillion miles, or about 9.5 trillion kilometers.
There we go. So it's a long distance. So the Milky Way has a volume of about 17 trillion cubic light years. All right. So let's look at some possible values for these numbers and figure out how many civilizations there are out there. So looking at that top one, n equals, and I put in the lowest rate of star formation that we think that we've observed, which is about 1.65 solar masses per year. I put in that each of those stars has at least one planet, and that 2 of them would be in a zone where it would be habitable. And give people go, oh, wait, that's not very likely. Well, Venus is on one end, Earth is in about the middle, and Mars is on the far end. So we've got 3 in this solar system alone that are in or very close to that Goldilocks zone. So 2 is not an outlandish figure. So then I put in that of those planets that are in the right place, roughly 0.8 of them develop life, that about 0.02 or 200ths of them develop intelligence, and half of that develop communication. To me, intelligence is a filter, by the way, getting back to the whole idea of the Fermi paradox. Some of the answers, the Fermi paradox is a statement done by Enrico Fermi. He asked the question, where are they? If there are aliens out there, why haven't we heard from them? Where are they? And the answer to some of those, some propose that there are filters. And life forming in the first place may be one of those. May be very rare. Okay? Intelligence may be another one, and I think it is, because your brain is about a 3-pound lump of, as I've heard it described, of soggy wet bacon, because it's a salty, fatty mess, and it burns about 1/3 of your calories that you take in every day. So if that doesn't provide a good, strong survival advantage, it's not going to develop in the first place.
Okay, Robert, I got to stop you there. Does that mean I can lose weight by just thinking harder?
Theoretically, yes, you could.
Good. I'm going to try that.
Yeah, I think you'd really be a slow loss, but I think it would be there. But,
Okay. You can
all right.
continue.
And then I put in the figure that every civilization that develops communications is broadcasting for about 100 years. That's about what we've done, and as we've discussed, we're going radio quiet now. So even though we haven't wiped ourselves out, we're still only being broadcasting for about 100 years where we could be detected. With those numbers, there is 0.053 civilizations inside the Milky Way. What this means is that any such civilizations are temporally spaced from each other. They are not spatially spaced. You can't go 1,000 light years in one direction and find one. They are actually just don't exist at the same time. Or they're not broadcasting at the same time. Okay? So that is one possibility. We're the only one broadcasting right now. Either because we're the only one that's had developed, the others have wiped themselves out, or they haven't developed yet. That is a possibility. So then I broadened the numbers a little bit, changed them up a little bit. I put that there's, kept the same star formation rate, but I put that there's 1.2 planets per star, kept the figure that there's 2 in the Goldilocks zone. But this time I put that every single one of them in that Goldilocks zone produces life. Now, as we've discussed also, this could be bacteria, microbes. It does not have to be complex life, but every one of them produces life. Of those that produce life, half of them produce intelligent species. Of that, those that produce intelligent species, 100% eventually become able to communicate in radio wavelengths, but again, they only last about 100 years, or do so for 100 years. And now there's suddenly 198 in the Milky Way. Well, that's kind of neat. How far apart are they? So how far away would we on average probably have to look? Well, they'd be around average around 2,700 light years away from us. So 2,700 years to travel there at the speed of light. Yeah, we're not communicating with them.
Well, here's an interesting point of view on that. So imagine that our first signals that leak through the ionosphere and got out into space. So the atmosphere affects, AM broadcast and so on. And let's say, that made it out in the 1930s. We'll be generous here.
Okay.
So how far would that have traveled in all different directions?
Well, let's see, 70, 90.
So it's roughly 100 years, let's say. We'll
100
just
years.
round it off here.
Yeah.
So the furthest that those signals could have went out is 100 light years.
Right.
So if the average distance to the nearest civilization from us, statistically, is about 2,700 light years, we have like 2,600 years to wait before the signal, on average, would get to the next intelligent civilization.
And then they would have to have a receiver powerful enough, large enough to actually detect that weak signal. I don't think the signal would be above background noise, to be honest.
It'd be very, very difficult to detect such a thing. I mean, there's a lot of interaction with the interstellar medium. This kind of thing that happens. It's not like space is a pure vacuum in our Milky Way. That's not the case.
Right.
There are stars and dust clouds and so on that we can observe directly. So that all affects the attenuation of the signal itself. So in some sense, it almost becomes undetectable by the time you're out to about 2,700 light years from us, if you wait long enough for the signal to get there,
right,
theoretically, right, from the Earth. Unless we purposely broadcast a very powerful beam in a certain direction.
And then anything in that direction is probably going to pick it up.
Yeah, then that's different, of course. But of course, then you still got to wait the time for that signal to reach, on average, the next civilization.
And this kind of brings up a point I always point out to people about trying to communicate with ET. We send out a signal. It's 2,700 years there. They pick it up and go, oh, hey, there's somebody else here. Hey, guys, we're here too. And it's 2,700 years back. Okay? That's, 5,400 years.
Well, imagine that on your Facebook, you put the fact that you ate a sandwich for lunch, and yet that does not get posted for 2,700 years. Who really cares that you had a sandwich for lunch 27 years ago in the past by the time they get that information?
So I was going to point out that 5,400 years ago, the Middle Kingdom of Egypt, if I'm not mistaken, would have been still in power. Okay? So, the reason I'm pointing this out is because a lot of people ask, okay, why are we bothering with this? It's pointless. It's wasteful. We're not going to engage in a meaningful dialogue here. And you're right. But isn't it nice to know that, hey, we've got brothers and sisters out there somewhere, or cousins or something like that,
In other words, we're not alone.
It's information, it's knowledge. And I'm sorry, I'll argue, it's a hill I'll die on. That knowledge for knowledge's sake is a good thing.
Right.
So,
now, your most optimistic calculation.
My most optimistic calculation, and this is not the most optimistic, I'll get into that in a second, but I essentially kept the numbers similar, except I bumped up the lifetime of the broadcasting civilization up to 500 years. And when you do that, you get 924 civilizations. Sounds like a lot. I mean, it's a lot more than 198. That's certainly more than 0.053. But that would still put them at 1,638 light years away from us. Okay. Yeah. And it's because of that whole thing of, to arrive at those figures, I assume the galaxy is a sphere. I will admit I made that assumption. It makes the math easy because the volume of a sphere is 4/3 pi r cubed. So the problem is that distance apart scales as essentially the cube root of r.
Right. I mean, that's an approximation. We're just working with approximate numbers anyways.
Right.
But here's a line of thinking. What is the nearest planet to our sun outside of our solar system?
Alpha Centauri.
That's right. How far away is that system?
4.3 light years.
Okay, so a little over 4 light years. So there's been plenty of time for our signals to leak out into space to reach the Alpha Centauri system.
Right.
And so if there by chance, right,
Mm-hmm.
happen to be intelligent life on a planet that's orbiting one of the stars in the Alpha Centauri system, and they advance to the point where they can detect our signals, even if they don't want us to know they're there, so they're just in this mode of listening, that would take place. They'd be able to do that.
Right.
So, but then if their normal sort of society, they bleed off signals, let's say they have radar, it could be weather radar if they need that on their planet and all this kind of stuff, that would leak out into space accidentally anyway, just like our military radar leaks out into space.
Right.
And so we'd be able to detect potentially those signals from here. And when we get those signals, they just left about 4 years ago. So it's relatively new when you think about it.
Right.
But if we don't look, how do we know?
How do we know?
So that's the argument one would make for SETI, because you could think, oh, the chance of seeing anything is just so remote, why even bother doing the experiment? Yet we just don't know for sure.
Right.
This is all from a statistical point of view.
It is. And in fact, Frank Drake's numbers he liked to put in yield about 10,000 other civilizations in the galaxy with us. Well, then they're a lot closer.
Yeah.
Okay. The end result that I like pointing out at this point in the conversation, though, is that really this whole thing scales with capital L. The longer they are broadcasting, the more likely we are to pick them up, the more likely we are to know they're there, and vice versa. So we're back to that question. Do we broadcast and let them know we're here, or do we keep quiet?
Now, from an energy point of view, the easiest thing would be just to listen.
Right.
Right? That's a passive way of being involved. It doesn't take that much energy. We're not broadcasting in space. We're just trying to receive any stray signals that happen to come our way. And so that's probably, and everybody could agree that that's not going to harm anything. There's no chance of things happening at that point, right?
Right.
So that would be one way to do it then, is just to passively listen, at least for a while. Maybe if we detect some signal that comes from a planet that's 100 light years away, then we could put together, some kind of package of information, if everybody agrees what's in that package, and
Right.
send that off, beam that to that location type of thing. So that would make a lot of sense in that point of view.
Right. And something I saw recently, so bringing it back to recent topics, is one of the solar sail projects that are going out. We're talking about how, especially with NASA's new progress on nuclear engines, with a nuclear engine to get it going, and then a solar sail, we could actually reach the Alpha Centauri system in roughly 40 years. Now, this is not with astronauts, folks. This is with a Voyager, a probe that we send. This is also it not slowing down. That would require fuel or acceleration on the other end. We're talking doing a flyby of the system. And, well, what's the use of that? Well, again, we get to look at another planetary system, another solar system than our own. What does it look like? What's really going on there?
Now, Robert, how do we know that there are other planets in orbit around other stars?
There are two main methods that I'll go over first. One is called the radial velocity measure. Basically, we use the Doppler shift and the spectrum of the star to determine if it's wobbling. In other words, it's radial motion towards us and away from us, because a star is being tugged on by its planets just as the tugs on the planets. So that produces a wobble in the star. And if that wobble is along the line of sight to us, those spectral lines will blue shift and red shift just a little bit. And we can pick that up. Okay? We can use that method. I think we're good enough now to get down to about a little smaller than Neptune sized planets. It's still not exactly where we're looking for. The next method is transiting. In other words, if the line of sight, if the orbit of the planet goes in front of the star's light will dim for a little bit. And having done a few shot the light curves, as they're called, for a few transiting planets, this is a wonderful experience because here's the light of the star, goes straight, it's steady, and then all of a sudden it drops. Then it goes flat for a little bit because the planet is much smaller than the star. So it goes flat as the planet gets in front of the star and stays there for a little bit. And then it comes back up to where it was before and goes back flat. There is no doubt this is a planet going in front of a star because stars are about the same size as each other. So if it's a star, it'd just be this V. But with a planet, it gets this flat bottom. And it's really neat to look at. And so we can determine that there's planets there using that method. Other methods, the minor methods, we can also do a method called astrometry, where we actually plot the position of the star and can see it zigzagging and wobbling around. And another one is gravitational microlensing, where the planet's gravitational field warps space-time, gets in front of the star brightens actually a little bit, and things like that. The other one, of course, was the actual first planet was found around a pulsar because it was affecting the timing of the pulsar's signal.
Because of the motion of the neutron star, the movement of it through
Right.
it. But then, of course, there's the direct method.
Then there's just taking a picture.
You just take an image of a star and you put a little blocker in front of the star so the light doesn't saturate your camera. And if you see some star-like faint things that are in the vicinity of the star, you just keep taking an image every couple months, let's say. And if you see those objects moving around such that they seem to be in orbit around the star.
I forgot about that.
Yeah, that's the direct method, right?
Guess what James Webb is doing right now, folks?
Right.
It's spotted a few planets that way.
Yes. So that has been done several years ago. It was kind of the first,
The first one was
discovery.
a few years back,
Yeah.
right.
So we can actually see planets orbiting other stars by direct imaging.
Now, I will put a caveat on that. We can see the planet. That does not mean we can see its clouds and cloud bands and everything like you can when you look through a telescope at Jupiter. All it is a dot of light. But it's a dot of light going around another star in a way you would expect a planet. Guess what it almost certainly is? Another planet.
Right, and so for that type of situation, you can determine roughly or make approximate calculation of what the conditions would be like on that planet. You can get an idea, for example, about how far away it is from the host star, how much energy it would receive from that star, to estimate, what would be the typical ground temperature or climate that would be on that planet. Very rough estimates, but of course to see whether or not water would exist, for example, so H2O would be in a liquid form, all these kind of things. So you see a lot of that speculation in the media.
Yes.
But people should know that we can't tell if there's dinosaur-like creatures roaming a particular planet or not.
Right.
But we have sniffed the atmosphere of some of these planets.
Yes.
Do you want to talk a little bit about that?
I can only talk about what I know has happened, which I know we've detected such things, of course, in some of these what are called hot Jupiters, where it's a Jupiter-sized or larger planet that is in an orbit that's, relatively speaking, for the size of the star, as close or closer than Mercury is to our sun. So these are very hot planets. They're very large gaseous planets. We've detected iron oxide, titanium oxide, sulfur, silicon dioxide, so SiO2 quartz in their atmospheres. Okay, so I know we've done that. I know also we've detected carbon monoxide, carbon dioxide, and now water in the atmosphere of a planet.
So the way it would work is that when the planet is in orbit around the host star, if the alignment is such that the planet goes behind the star relative to the Earth, then we can't see that planet for a period of time until it reappears on the other side of that star. So while the planet is behind the star, we can do detailed measurements of the light that's coming from the star. We can look at its spectrum at high resolution and get an estimate of the abundance of various elements and molecules, if they exist, depending on the temperature of the star and so on. And then when the planet reappears and passes in front of that star, the light from the star atmosphere, which we know now and have measured in great detail, as that light passes through the atmosphere of that planet on its way to us, then we can see the difference in the spectrum of those two situations.
And then compare that to known molecules and elements.
Right.
And bam, you've got the spectrum of the atmosphere of that planet.
That's right. So it's a way of probing then the atmosphere of that planet.
Right.
It's almost as if you're using a laser beam to probe dust clouds in a room. You know, the laser would reflect off those dust clouds, and that'd be a way to tell you where it is spatially and so on.
And so that brings up the point. People have probably seen the reports of water world discovered around another star. How do we know that? Well, again, that transiting method, we know the size of the planet because we can tell that from how much dimmer the star gets. With transiting method and the radial velocity method, which if it's passing in front of the star, it's in line to give us the radial motion, we can get the mass of the planet. Well, if you know the mass and you know its size, hence its volume, you can get its density. And from the density, if it's, like the average density of Earth is 5.2 grams per cubic centimeter. To put that in perspective, water is 1 gram per centimeter cubed. Okay? So the Earth on average is about 5 times denser than water. And not heavier, denser than water. So what we've done is we found a few of these planets, most of them usually what we call super Earths, so about 2 to 3 times the size of Earth. And what we find is their density is 2.5. Well, what do you make of that? It's a lot less dense than rock or metal. So what's left? Water. So a good component of it must be water, and hence we call it a water world.
In fact, we use that to look at the composition or infer the composition of moons orbiting various planets in our own solar system, like moons going around Jupiter and Saturn and so on.
Right.
We can get a measurement of their average density and infer what is the amount of water, whether it be in ice form because it's so cold potentially, or you could have a situation where you have an ocean that's deep inside of the moon itself.
Now I'll ask that.
Yes.
How do you know there's an ocean underneath all that water ice? Like with Enceladus.
Right. So one of the things you can do too is look at the heat output coming from these objects. And that's one way to know that they're getting the geothermal heat is efficiently enough to keep the H2O in liquid form.
Right. And another way, since we've had satellites around Jupiter and now Saturn, with Cassini and Juno, you can also take magnetosphere measurements, and you can see how the moon affects the magnetic field of Jupiter. And what we found is that it is affected like what you would expect if the moons had a fluid-filled cavity underneath the ice crust. And so we're looking at that sort of thing now.
And the other thing you might wonder is maybe there's a very low mass star or an object that's not quite a star, which we call a brown dwarf, that's in orbit around the brighter star, the more luminous object. And maybe that's what we're seeing rather than evidence of a planet. But
Right.
when planets are going around stars, the other thing that does, it actually reflects some of the light given the alignment, and you don't expect light to reflect off of a star.
Oh, good point.
You know,
Excellent point.
So that would discriminate between those two type of objects as well.
Right.
So that
So-
helps. But so far the evidence is we have over 5,000 exoplanet objects that have been detected.
So I'll bring
Yeah.
up this. Sorry about that, folks. Technical glitch. I forgot to add our microphones on this thing, this slide. So we've got 5,000 candidate extrasolar or exoplanets. And so these are all candidates for turning our radio telescopes, our ears, to listen to them. Because these are systems with known planets. Maybe one of them, or maybe in the case of a Jupiter size, maybe one of their moons has life, and maybe that life is broadcasting. So, yeah, these are all targets for the SETI program, as I understand it, right?
Yeah, I mean, the other thing too is this is accumulation of data over many years, from various missions. The greatest one that's up there now is the TESS mission, the NASA mission. And there's been others in the past, like the Kepler mission that's gone up in space and made very accurate measurements of the change in the light of stars to infer that some object is transiting in front of that star relative to us,
Right.
and then moving away and back in the backside type of thing. So you see the periodic dip in the light, or the light curve, as we say, the measurement of that for different stars. So you need a very precise measurement then of that light output to get that. And so that's better done in space where you're not affected by the Earth's atmosphere.
Right. Or city lights. But we've had that discussion already as well. Maybe we need to bring it back up again sometime, but not today.
And the other thing to notice on this slide is that this shows the all-sky projection of these extrasolar planets, the candidates anyways. Some of these would have to be confirmed.
Right.
And there's a lot of follow-up work that ground-based telescopes are doing nowadays. In fact, it could be a job for anybody to do that, right? You continuously try to follow up these detections.
In fact, anybody interested in it, there's ETD, the Exoplanet Transit Database, that they actually actively collect observations from so-called amateurs as well as professional astronomers to confirm these targets of interest, these TOIs.
Right, and when you look at the all-sky view that you see here, which is what's shown, this sort of Antoff type of projection, as it's called, we notice there are certain preferred regions in the sky. That's because that's where the instrument, the space telescope, is concentrating, for example, looking in various regions.
Right.
And one thing through the exact middle, of course, that would be the plane or the disk of our Milky Way galaxy. And there's a high density of interstellar matter, both gas and dust. And that affects, think how far you can see with a given telescope, and at least in the optical.
Right.
And so we always have to worry about those type of selection effects.
And to put an analogy that most of you may have probably worked with on what the effect of gas and dust in the way is, think about how well you can see on a foggy day. You've got little particles in the way. Space is a lot bigger, so even though it's rarefied, we've got a fog in the way in those directions.
Right. So the interesting question then, when we talk about life as we are focusing on this podcast, is how do you go from something that's not alive to something that's live?
Oh, Lord.
And not only that, clearly it happened here on the Earth, but is the means of getting there so general, so universal, that we would expect those conditions to be available in multiple locations throughout our universe?
Okay. I've got an argument for both sides.
Okay, let's hear.
Okay. The argument for the negative side, that it's a rare event, is where's the rest of the life in our solar system? Mars is dead. So far, Europa's dead. Enceladus is dead. And these are just the candidates. Venus is dead. Jupiter's atmosphere is dead. These are just the candidate probabilities in our own solar system.
Now, when we talk about life and you're saying it's dead, are you ruling out, when you say that, not even microbial form of life?
I am ruling it out for now.
Okay.
For now.
Right, because to know for sure, we have to do the
Right. We need to go sniff the ground.
right. We have to do the experiment, do the
There you
observation. We have to go to Mars, analyze the soil and stuff, and see if anything is alive. Maybe it's several inches under the surface to protect itself from the ultraviolet light that bombards the surface of Mars, for example.
There you go.
And so bacteria, Martian bacteria, then is found once you dig a foot down or something like that, right? But we know because we have landers. Several landers. We've had spacecraft land on the surface of Mars. And when they photograph, I don't remember seeing the big M anywhere.
Right.
So clearly there are no fast food restaurants that we know of on Mars. So, you can start with the very silly example, but then work your way down, basically using the power of observation and experiment to try to get an idea of what form of life could be there, and maybe none at all, as you suggest, is the most pessimistic view.
Right.
But then continue your analysis, Robert.
Okay. So on the negative side too, I'll point out what a friend of mine pointed out, because it's always been said, oh, maybe there's life on Mars, but it's just clinging on. And this brings up the positive side of my argument as well, and that is everywhere we look on Earth, there's life. You go kilometers down beneath the soil into the rocks, and there's microbes. You go down to the bottom of the ocean, there's microbes. You go to these things called methane seeps. Methane seeps at the bottom of the ocean, completely inhospitable, kills everything else, but there's still microbes in that methane. Okay, so there's life everywhere. Life does not hold on by its fingertips.
So these are
It's there or it's not.
So these are the forms that we would call extremophiles.
Extremophiles. So the positive argument is that everywhere we look on Earth, there's life. So life must be able to form in even what we would consider inhospitable conditions.
Now, do you remember Bill Clinton? You know who that is?
Mm-hmm. I remember him.
Okay. Do you remember that sometime back in the 90s that he came out to do a press conference and he warned people not to get too excited because we have to confirm these experiments, these observations? Do you remember what that was related to?
Some meteorites that were purportedly and have been convincingly found to have been from Mars at one point.
Right. So it was a meteorite that was found in Antarctica, and that meteorite came from Mars. Now, people might wonder, how do we know that it came from Mars? Well, it's interesting because in the 1970s, we landed Viking 1 and 2 on the surface of Mars. They included instruments that would sniff the atmosphere. So we have a very good observation of what the atmosphere has in terms of its composition. And inside the meteorite that we found in Antarctica, we discovered there are gas bubbles, trapped pockets of air. And when we analyzed the composition of that air, you know what was discovered?
It matched Mars.
It matched the composition.
And I will point out, having come from a planetary science department at one point, the chemical composition, the isotope composition of the oxygen in the meteorite matches Mars.
Right.
So.
And in the analysis of that rock, what was discovered was it looked like fossilized remains of nanobacteria, as they were called at the time. So very small things that you need, really, special instruments to see. And the idea was that these nanobacteria then actually came from Mars. Of course, that's the connection.
Right.
So people got excited. That's why even Bill Clinton got in the act as president of the United States at the time. But the years since the 1990s when this came out, that kind of went away, the excitement, right? So there's been a lot of controversy, I think, on that study. And I think what we really need then is and we can do this, we have the technology, we've had it for a long time now, is we need to have, and the cheapest way to do it would be for a robot to go to the surface of Mars, to gather some rocks, so we know that they came directly from Mars. They're not contaminated by laying in Antarctica for millions of years, as we suspect this has happened, right? Like the meteorite that I'm talking about, that we talked from the 1990s. That we can go there, go to Mars, and actually look at the composition to see if there is nanofossils, from bacteria in those rocks.
Right.
And that's something that NASA has been planning to do, and there are plans now to do that. The latest estimate I heard is in the 1930s, the 2030s, a little off by 100 years there.
Yep.
In the 2030s, in fact, Perseverance rover that's on Mars now is actually gathering up some interesting rock and soil samples and leaving at different places on the surface of Mars. So this is something, like I said, we could have done many years ago and didn't do it, but hopefully that will happen in the 2030s. Hopefully it happens soon, so I'm still alive to be able to see the results of this.
Right. But again, we're back to the point. We're looking for fossils of these microbes because there's absolutely no evidence really that they are still there. And as my biologist friend pointed out, if they're there, they're going to be there.
Right.
They're not going to be just clinging on by as the saying goes, by the skin of their teeth. They're going to be there and have adapted to this environment, or they're going to be wiped out.
Right. So if you're interested in that is thinking about life and where it comes from. If you're interested in biology, if you're interested in chemistry, there's a lot of chemistry that you have to deal with. If you're interested in astronomy or astrophysics, one of the things, if you're a young person in high school, is please consider coming to the University of North Dakota. We have a lot of interesting programs and departments here on campus where you can get involved in a lot of this type of work and STEM work, and then get a good, thorough foundation under your belt before moving on and doing other things, whether it's working for NASA or otherwise.
Right.
So I think this is a good time to end. It was a very interesting discussion today. Just to remind you that our next podcast will be a week from now, so that's on February the 21st at 3 p.m. Central Standard Time. And as always, we like to leave a quote. This one is related to life, so it fits in. This is actually a quote from Edward Robert Harrison. And the quote is, "Hydrogen is a light, odorless gas, which, given enough time, turns into people." Thank you for listening.
Thank you, folks. Hope you enjoyed it.